So right. So integers are represented in different ways. But there is only one set of integers, right? So the differences on the representation. So for example, the usual default representation is the decimal representation, in which you write 0, 1, 2, 3, 4, 5 up to 9, and then you have 10, 11. So using only 10 symbols, namely 0 up to 9. Yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Of course, you could represent the same number using 2 symbols, so you have binary representation, or 8 symbols using octal representations, or even 16 symbols, namely the hexadecimal representation. So let's see a few examples. Let's write the binary representation of 21. Then this should be very easy. This is 21 is, of course, you simply mod, you divide it by or you write it using division algorithm. So you divide it by 2. So therefore, you have this is actually 10 times 2 plus 1, and then 10 itself is 5 times 2 plus 1. Sorry, 5 times 2 plus 0, and then 5 is 2 times 2 plus 1, and then 2 is of course 1 times 2 plus 0, and then 1, well, 0 times 2 plus 1. So therefore 21 is actually, well, start from here, 1, 0, 1, 0. All right, binary base. Yeah. Now you could also convert the other way around. You start from an octal representation, for example. Here you want to get the decimal representation. So what do you do? If this is a base 8, so this is actually 3 times 8 to the power of 2 plus 2 times 8 to the power of 1 plus 6 times 8 to the power of 0, right? So that would be 3 times 64 plus 2 times 8 plus 6 times 1, which gives us this is 92 plus 16 plus 6, which gives us 214. Yeah, so that's how it works, right? So now let's give another example. If we want to write this as a binary, so what would you do is, well, 14 is, well, 107 times 2 plus 0, and then 107 is 53 times 2 plus 1, and then 53 is 26 times 2 plus 1, and then 26 is 13 times 2 plus 0, and then 15 is 6 times 2 plus 1, and then 6 is 3 times 2 plus 0, and then 3 is 2 times 1 times 2 plus 1, and then 1 is, of course, 0 times 2 plus 1. So you get that 2014 is equal to 11010 110 base 2. Yeah, I hope this is correct. Yeah, I think so. Yeah. So hold on a second. Let's see. Yes, that is correct. Yeah. So that's the representation of numbers. So I think this is simply a repeat of what you've seen in high school. I think so. Yeah. Now, so this is the general theorem. Essentially, every positive integer can be expressed uniquely in the form of in the base of choice. Like you choose a base. Yeah. So that means it doesn't have to be 10 to 8 or 16. You could have like base 20, base base 9 or whatever, right? This is the algorithm that I use. So this one actually, so this example use this algorithm, and then well, this is another example. You could simply do that. Well, you can simply run this, or you do it the same way as I had earlier. So for example, this, you want to convert this into octal, which is base 8. So therefore, what you do is you divide this by 8, right? So you divide this by 8, which gives you 6, 48, 6, 33, so 7, 56, and then you get 7, and then 2, which is a 9, 2, yeah, and then 1. So let's check. So is it 30 times 8, which gives us 7. So should have been 0, right? 0. Yeah. 56 plus 7, 3, 6, 4, and then 0. Yeah. So yeah, so that means this is what 6790, 6790 times 8 plus 1. Yeah. And then again, this is what? Well, let's just do that. Well, this gives us 8, 64, 3, 9. This is 4, 3, 2, 6, 7. Sorry, 7, yes. And then this gives us 8. Yeah, 64, now 6. So that will be this plus 6, and then of course 848 is 106 times 8 plus 0, and then of course 106 is 12, 13, I think 13, yeah, times 8 plus 2, yeah, and then 13 itself is 1 times 8 plus 5, and finally 1 is 0 times 8 plus 1. Yeah. All right. So that gives us the resulting base 8 expansion. This. Now let's check. All right. I hope this is correct. Yeah, I think so. Yeah. Yeah. Good. This is basic. That's how we convert this into an octal expansion. We have it here. Yeah. How about this one? Again, we have examples. So get divided by 16. You have that, and that, and that, and that, and that, right? So that means what you have is this, right? 5, 5, 0, 15, 15, and 11, right? Now, of course, that means you must take this F, this is F, and this is B. Yeah, remember, if the remainder is 10, then you have A, 11, you have B, 12 you have C, 13 you have 13 you have D, and then 14 you have E, and then 15 you have F. So that's how hexadecimal works. Yeah. So therefore, the hexadecimal representation of this number is this number. Yeah. So remember, these two numbers are the same. So they are the same integers, exactly the same integers, but only written in different ways. Now, there is a shortcut if you want to convert binary to octal or hexadecimal. Yeah. Well, one of course, one way is to convert the number first into this decimal expansion, and then the result is converted into the base, the second base B to expansion, for example. So for example, if you start from base 8 to base 2, then you convert the base 8 representation into decimal expansion, and then convert the decimal expansion into a binary representation. But we could of course have a shortcut if the base is the power of 2. This is power of like this. Yeah. So for example, here if I have binary expansion like this, then converting this into an octal expansion is simply done by taking 3 digits at a time. So you take 3 from the right, yeah, and then you take 3 from the right, and then 3 again, and then 3 again, and then now you have 2 here, so you add 0 here. Yeah. Yeah. So therefore you get this. Yeah. Similarly for base 16. Whereas the other way around, if you have this octal expansion, to have a binary expansion, what you do is simply convert this into binary, this and this into binary, and then you concat them together. Yeah. That's how we work on the integer representation. Now, finally, for the modular exponentiation, this can be done by following the algorithm, which of course given there. Yeah, I think we have it here. Hold on a second. Yeah, here we have the algorithm, but here is how it works. Yeah, first, what you do is, let's just do this example, all right? So you take the power here, yeah. You take the power of this, and first, what you do first is convert 644 into binary. Then you have what is 644? Can anybody give me an answer in binary? 644 is what?
644 in binary, sir.
Yes.
10 10 000 100.
Which is, yeah, this base 2. Yeah. So that is this. We could check, right? So this is 0, 1, 2, power of 2 plus 3, 4, 5, 6, 7, power of 7 plus 8, 9, so 9. So this is 4, this is 128, this is what was it? $512, right? Yeah, that would be, yes, second 44. Yes, correct. So we have this, yeah. Let me just delete this, yeah. So it's clear. See, now what we would do, we start with the We start with the let's have a look at the variable. So the variables are x. You have x. You have p, and then you run from the right. Let's say run from the right, from here, there. Yeah, you run from the right. Yeah, check the digits. Yeah, if the digit is 1, then you multiply x with p and perform a modulo with m. Yeah, the m here is the modulo. Yeah, you want to call the modulo here. Yeah, whereas if not, well, if it is, you have that. If in any case, you also need to multiply p with p itself and then modulo m. Yeah, so here's what we do. We start with x. Yeah, x first is 1, and then p is what? B mod m, right? So let's see. B is here in this case 3. Yeah, 3 mod 645, right? Which is 3. This is our first step. Now next, you go from left. Yeah, yeah. You go from left. You start with a0. A0 is 0 from here. Yeah. So therefore, you only update what? You only update the p. Yeah. Yeah. You only update the p. So p is then, you have 3 here, right? So 3 square mod 645. Yeah. Which is 9. Yeah. A1 is 0 again here. So p is 9 square mod 645, which gives us 81. Now what we have is then about A2. If A2 is 1, remember you go from right to left, right? So here is A2, it is 1. So therefore, not only P, but also X. So you update X first before you update P. X is actually X is 1, right? 1 times, what is P now? P is 81. So 81, yeah, mod 645, which gives us 81. Yeah. And then of course P, you square it and mod 645, which is 6561 mod 645, which is of course 111. All right. At this point, any question?
No, sir.
No? Okay. So let's move on to the next one, right? So A1, A2, we have now A3 up to 4, 5, 6. Yeah. A3 is 0. So therefore P is square mod. Remember, only square it, right? 645, which is 12,321 mod 645, which gives us 66. Now then A4 is also 0, so therefore P is 6P6 mod 645, which gives us 4356 mod 645, which gives us, of course, the result is 486. Now A5 is 0, so therefore P, you compute P like this, you square 486, and you have 236,196 mod 645, and you compute that, you get, of course, 126. Now A6 is 0 again. So P is 126 square mod 645, which gives us 15,876 mod 645, and this is A, and this guy gives us the result of the mod is 396. Yeah. So you see now the pattern, right? So every time you see the digits of the binary expansion of the power is 1, you go from right to left, then you update X. If not, and in any case, whether you see a 1 or a 0, you always update P. So P, the way you update it is squaring it and then perform a modulo operation of it. So therefore now we have A7 is 1 now. A7 is 1 here. Now what we do is then, remember what is the last value of X? This one, right? X81, right? So therefore X is 81 times P, the previous P here. Yeah. So 396 mod 645, which is of course here is can anyone compute this? Let's just use calculator here to make it quick.
32,076.
Correct. So 376 mod 645. If you compute the mod, then you get the result is 471. Now, of course, P must be updated as well. So you have not the P here. Yeah. Oh, well, it is the P there, right? So 396 square mod 645, which is 156,816 mod 645. This is 81. Now A8 is 0. So P is 81 square mod 645, which we already seen, right? Which is 111. Yeah. Yeah, this one. And then of course A9 is 1, which gives us X to be what is the previous X is 471 times P 111 mod 645, which gives us 36. So now we're done. So the result is 36. Yeah. Any question? Any question? No?
No, sir.
No? Okay, good. If not, I think it's just a matter of following the steps there, right? So let me check the reflection that you've submitted. Some of them are, well, some of you are worried about error in calculating modular congruence. Well, for example, for this one, yeah, for this calculation, of course, if you simply put the question into a calculator, you will get the answer, right? But I think in our class, we also want you to be able to elaborate the answer or the steps to reach the answer this is something. The point here is that you know how this is computed in a machine, yeah, in computer. Actually, that's how the operation is done in computer, yeah, in a sense, yeah. So we want you to know about that, and be able to simulate the computation. But of course, if you, for example, this one, you want to compute 396 square, for example, then by all means use whatever means you have, yeah. Yeah, you don't have to write compute everything on paper, yeah? So for example, for this type of problem, this is the expected answer, yeah. All right, now we also have a question on quiz number 6, so we will talk about that later when we talk about the GCD. I also see a question about congruence classes. Okay, what is congruence classes? Congruence classes is simply a set where you collect together the numbers or the integers with the same remainder when divided by a certain number. So, example, this one. So, congruence classes is always defined in terms of modulo sum integer. So, for example, if I have a, let me use which space I use. Let me use, like, if I want to say congruence classes classes modulo 4, for example, that means, yeah, from the set of integers, you divide them into those that has 0 as remainder when divided by 4, yeah. And then those that has 1 as remainder, those that has 2 as remainder, and then of course those that has 3 as remainder. Now, let me ask a question. Why do we only have this for classification? Why not those that has 5 as remainder, for example? Can anyone answer that?
Because when it's 5, you modulate by 4, it'll get 1 as the remainder.
Well, that's correct. So essentially, if you wanna collect those integers that have remainder 5 and divided by 4, then essentially it's the same as those integers that have 1. That have 1, yeah? That have 1 as remainder when divided by 4, right? Yeah. So that means, well, that means you simply collect them together, right? So for example, in this case, what are the numbers? Well, the numbers are, of course, example, there are many, right? -8, -4, 0, 4, 8, and so on. Yeah. What about this one? You have many. You have, for example, -9, -1, 3. Sorry, not -9. -7, I should say. -7, -3, 1, 5, and then 9. What about this one? This one is -6, -2, 2, 6, so on. And finally, last one is -5, 1 and then 3 and then 7 and so on. All right. So now, of course, you have 4 of them. You have 4 sets, 4 classifications here, and you want to give name to them. Yeah, you want to give them name. So, well, the way we give them name is you simply pick any member of the set and use the this square bracket notation. Yeah. So, for example, this I simply take, for example, this is as a name. Yeah. What this one? This is name. This is this one, and then this is. Of course, you could simply pick other names, right? For example, you can also pick this, yeah, which is fine as well. Yeah. Yeah. Any question regarding congruence classes? No. Somebody asked a question on rank mode, but I don't get the questions. I don't know what rank mode is. So if you are asked these questions, let me know, and we'll talk about it. Okay. Now for the rest, there are questions on or sort of general difficulties on modular arithmetics. What you would do is well, the idea here for our modular arithmetic is simply just perform the arithmetic as usual, like multiplication, addition is as usual, but make sure the result of the operation has the correct remainder. Yeah, that's the only thing. Okay, I see a question on modular exponentiation. Modular exponentiation. Okay, there is a question on how it affects the remainders when we manipulate equivalence. Well, I think you meant this. I think this is probably the question. Yeah. So here's the thing, right? With modular arithmetic, you could add, you could multiply. If you could add, you could also subtract. Yeah. But not divide. Yeah. This is the reason. Yeah. So here's the reason. Yeah. Okay. And you cannot exponentiate the numbers as well. Yeah. Yeah. So I think you see the example. So 8 is congruent to 20 modulo 6, but 2 is not congruent to 5 modulo 6. So the point is you can do add, addition, subtraction, multiplication. That's the thing. All right. So we have a question on how to prove theorems, do's and don'ts of proving theorem. Well, proving theorems mean that you have to go through you start from the premise and try to come up with the steps to reach the goal, right? So I don't have a specific do's and don'ts. The only thing is exercise a lot, looking at examples of proof in the book. Yeah, looking at examples of proofs in the book. Some questions in the exercises have solutions at the end of the book. Yeah, you could consult that and see that to get inspiration on how to prove things. Yeah, but do's and don'ts, well, just be careful and making sure every step is or can be correctly inferred from the previous step. So from one step to the next, you have to be sure that every step is correct. Then you get the correct answer. Yeah. All right. I think that should be generally the generally is okay. Now, well, somebody asked confusion on using which theorems are useful. Well, when proving, right? So when proving, essentially every theorem you have at your disposal is useful. Now, it's hard to say depending on the question, right? So, so you have to try it out, like you see whether it goes anywhere or not. Like that's how I work out my proofs, and see the, and then usually if you practice a lot, then you will get a hang of it. Yeah, you will get a hang of it in determining whether this theorem is useful for your proofs or not. So that's the thing. Now, a question on modular exponentiation. I just want to make a remark here. Modular exponentiation is not, you can, here's the point. When the question is on modular exponentiation, you do not have to use tables, all right? You don't have to use tables. You can also use, you can also solve the questions without tables, without writing down tables, right? I hope that sums up the my response to the questions on the reflection. Any question before I move on to the next set of materials? Does anyone have any question?
No, sir.
No. If not, hold on a second. All right, so let's move on to the next part of the lecture. This is the old slides on that, but I'm still using the same slides. I'll try to update this later on a little bit, but the content is the same. Now, the next part is talking about primes and GCDs. All right. So, why? What is your impression on prime numbers? Can anyone give like opinion on that? What makes prime is interesting? What makes primes interesting?
It can only be divided by itself.
Yes, it can only be divided by itself, or one, of course, yeah. Or here is this is the way we defined it, right? But more interestingly, actually, primes are the basic building blocks of integers. What I mean by that is that you will see later, every integer can be written as a combination of primes without exception. Every positive integers, or in fact every integers, yeah, every integers can be written as a combination of primes. We'll see that later. So this is very interesting. So it's like if you build a house, you have bricks, bricks. You build a house, you have bricks as the basic building blocks of a house, for example, then analogously you could say that primes are the bricks for integers. Now that's very interesting. Now, so what is prime? So a prime is an integer that has exactly two positive factors. So essentially, this is the key part, right? So it has exactly two positive factors, namely 1 and p itself. So it as you said earlier, it is divisible by itself and 1 and no other, right? Yeah. In no other positive integers. Yeah. Otherwise, you will say that an integer is a composite. So n is a composite if and only if there exists an integer a with 1 up to n. Sorry, with a is between 1 and n. So a is 2, 3, 4 up to n minus 1, such that a divides n. So it has a factor it has a positive factor other than 1 and itself. Now, of course, by this definition, 1 is not a prime. The integer 1 is not a prime because it only has one positive factor, namely 1 and 1 itself, right? So it's not a prime. And for all purposes of or results or theorems about primes, 1 is never considered a prime. 1 is an integer, but it's not a prime in this definition. So while prime is important, here is the thing. Yeah, here is the key part. It's called the fundamental theorem of arithmetic. So it says that every integer greater than 1 can be written uniquely as either a single prime or a product of 2 or more primes with duplicates allowed. Yeah. Such that those prime factors are written in an increasing order. So what are they? What are examples? So for example, 200 is what? Can we write 200 as a product as a single prime? Is 200 a single prime?
No.
No. Yeah. So therefore, it's a product of 2 or more primes, right? So what would be the product?
2 and 5
2 times 5, and then
times 20, times 20.
times 20. Okay. But 20 is not a prime. So
Yeah.
can we simplify that?
2 to the power of 3 times 5 to the power of 2.
All right. So good. Yes. What about this one? $641.
Is it prime, sir?
Is it? Is it prime? How do you know?
I can't divide it by 2 or by 7.
How do you? Why only 2 and 7?
Because usually the multiples of 7 has 1 at the back.
Why not 11?
Is it because we cannot divide it by prime numbers up to 25?
All right, that's great. Yes, actually, that's true. Yeah, so this is a prime. Thank you. Yeah. it cannot be divided by any prime numbers up to 25. Yeah, so that's great. Yes. So therefore, it is a prime. Now, how about 741? Hmm. 741 is what? Can we divide this by 7?
By 3, sir.
By 3, okay. 3 times 90, no, not 90. 3 times what?
247.
247. Okay, which is 3 times. Can we simplify this further?
13
Uh,
times 19.
13 times 19. Yeah. Yes. Great. So that's the product. Yeah. How about this one? 899. Is it divisible by 7?
It's divisible by 29.
29. And that is 29 times
31.
31. And we're done, right? So these are primes. Yeah. Good. Now, but the rest is easy, right? So this is actually equal to 10. So you see, every number or every integer greater than 1 can be written that way. Yeah. The proof of this theorem is beyond the scope of this class. However, you could have a look at the hint. I think at least part of the proof is also discussed in the book as well. I think when they talk about induction, mathematical induction, just read the chapter and you'll see. All right. Now this is the reason why the one way to check whether the number is prime is by checking whether it has a prime factor, whether or not, whether it doesn't have a prime factor less than or equal to the square root of n. No. So this is equivalent. This could be also said that if n does not have a prime factor that is less than or equal to the square root of n, then n is a prime. So how do we show that? Well, I think this easier. Let's start from this premise, and we show that this holds, right? So suppose n is composite. Yeah. So then there are different ways, right? So for sure, then if n is composite, then for sure, what do you know? What can we conclude? What can we infer if n is composite?
It is divisible by a prime number.
Yes, but what is the definition of composite? Let's see. right? So we use that definition, yeah. So if n is composite, then there is an integer a with 1 less than a less than n, such that a divides n, right? That's the definition, right? In other words, n is equal to a times b, right? Yeah, for some integer. Well, n is positive, right? So n, so integer b, yeah. Since, of course, n is positive, and a is positive, and a is less than n, then b is also less than n. Moreover, b is greater than 1, right? Yeah. Okay, so now that means n is equal to ab with a and b integers, and 1 less than a less than, sorry, comma b comma b, a and b less than n. Now what we want is, we want to show that n has a prime factor less than or equal to n. So now now note that either a is less than or equal to the square root of n, or b is less than or equal to the square root of n. Now, why? Because otherwise, if not, then what happened? Because otherwise, a is bigger than square root of n, and b is bigger than square root of n, right? Can you guys still follow me here?
Yes, sir.
Yes. In that case, ab is what? Is greater than what?
And
Greater than square root of n times square root of n, right? Which is n. Yeah, which is impossible, right? Do you know why is it impossible? Do you know why is it impossible? Why is it impossible that ab is greater than square root of n times square root of n is equal to n?
is it because AB is the factor of n?
ab is a factor of n, or to be precise, this one. Yeah, because we know that ab is n. Yeah. Whereas this says that ab is greater than n, right? So it's possible, right? You cannot have ab is greater than n and at the same time ab is equal to n, right? So we have that one. What we have is that, so that means n has a positive factor. Remember, a and b is greater than 1. Yeah, that is, and moreover, either a is less than or equal to n, or b is less than or equal to n. So therefore, n has a positive factor that is less than or equal to the square root of n, right? because at least either A or B, any one of them at least, must be less than or equal to the square root of n. Now, what's next? So we know now that n has a positive factor that is less than or equal to square root of n. Now what we want is to show that n has a prime factor that is less than or equal to square root of n, right? That's what we want. So we have two cases then, right? Case one, yeah, A or B is prime. Yeah. Or not just A or maybe not A or B. Let's do it slightly different. Guess one. You know that n has a positive factor that is less than or equal to the square root of n. Case one, that positive factor is prime. Is already prime. In that case, then we are done, right? Now, case two, of course, that positive factor is composite. In that case, what do we know?
We divide it with a prime number.
Why? Which
So
prime
that
number? So you know that n has a positive factor that is less than or equal to the square root of n. Now you have two cases. This positive factor, look at that positive factor. So either A or B, either A or B. That positive factor that is less than or equal to the square root of n, you have two cases, right? So one, that positive factor is already prime, then we are done. So that means, that means n has a prime factor that is less than or equal to square root of n. But now for case two, you only have that n has a positive factor that is less than or equal to the square root of n, and that positive factor is not prime. So it's a composite. Well, we want to show that n has a prime factor, right? So that means we use then by the fundamental theorem of arithmetics. What can we conclude about that positive factor? Must satisfy what? It must satisfy what? That positive factor is not a prime, so you cross this out. That means that positive factor is a product.
primes.
What is it?
A product of two or more primes.
Correct. So that means that positive factor is a product of two or more primes. Yeah. Then that means that positive factor itself has a prime factor, right? Yeah, which also is also a prime factor for n, yeah, which is n less than or equal to n, yeah, that is less than or equal to the square root of n. Any question? No question? No? So that is the reason why we could simply check whether the whether n has a prime factor or not, that is less than or equal to the square root of n. So here is the short part of the shortened description of the proof. Right? So for example, is 101 prime? That means what you do is, what is the square root of 101? Well, you don't need the exact number, right? You just need to know that this is bigger than 10, but less than 11, right? Yeah, square root of 100. Now, therefore, you check if 101 is divisible by, yeah, by any prime from 2 to 10. So, yeah, so check, right? So 101 is to check, right? So what are they? 2, 3, 4, 5, and 7, right? So that means you know that check. One is it 2? Does 2 divide 101? No, right? You know that 3? Does it divide 101? No. Does 5 divide 101? No. Does 7 divide 101?
No.
No. Yeah. Because all of 2, 3, 5, 7 do not divide 101. Then we conclude that 101 is prime. Yeah. So that's how it works. Any question? No? Okay, if not, we continue. So of course there is another way to a faster way, actually, slightly faster way to decide whether a number is a prime or not. We use a sieve of Eratosthenes. The way we do it, let me just give you an example. This allows us, for example, to find all primes not exceeding 100. So let's start with, so first of all, we cross out 1, of course. And then we start with the first prime, which is 2. We start with 2. Yeah. And then cross out all multiples of 2. So that means you cross this out, this, and this, and this, and this, and this, and this, and this, this, and this, this, like this. 62, 64, 66, 68, 60, 70, and then 72, 74, 76, 78, 80, and then 82, 84, 86, 88, 90, and then 92, 94, 96, 98, 100. Now, next, find the next number that is not crossed out. So, the next number that is not crossed out is 3. So 3 is the next number. And then cross out all multiples of 3 that is not yet crossed out. So from 3, we already crossed out 6. So the next one to be crossed out is 9, and then 15, and then 21, yeah, 24, 27, 30, 33, 36, 39, 42, 45, 48, 51, 54, 57, 50, 60, 63, 69, and then 75, 78, 81, 84, 87, and then 91. No, sorry, 87, 90, and then 93, and then 93, and then 99. Good. Now the next one, we start from the beginning, from the beginning, and then look at the next number that is not yet crossed out, which is 5. So therefore now we simply cross out multiples of 5 that is not yet crossed out. So they are 25, 35, 55, 65, 85, and 95, right? The 10s are all crossed out already. So the next number that is not yet crossed out is 7. So we cross out multiples of 7. So that would be, let's see, 49. 49, and then what's next? 77, right? Yeah, 77. Hmm. 77, and then 91. Is it 91? Yes. Yeah. 77 plus 7 is 84, plus 7 is 91. So yes, that is that. So then what is the next number? Not yet crossed out, there will be 11. We cross out multiples of 11s. They are all crossed out here, I think. Right? So that means the next one is 13. And of course, there is no multiples of 13 that is not crossed out. So every multiples of 13 have been crossed out. Similarly, 17, 23, sorry, 19, 23, 29, 31, 37, 41, 43, 47, and then 53, 59, and then 61, 67, 71, and then 73, and 79, and then 83, 83, and then 97. So those are the primes not exceeding 100. Any question here? Pretty easy. Okay, good. If there's no question, so let me continue. So how many primes are there? Well, there are infinitely many primes actually. Well, so let's start with this. Is it true that there are infinitely many primes? If you think about it. If you think about it, is it true that there are infinitely many primes? Can you think, can you guess, or can you somehow explain about that?
Because there's infinitely many numbers, then there will always be a unique number.
What do you mean by that? What do you mean? What unique number are you talking about?
Sorry, what, sir?
So you said unique number. What do you mean
Yeah.
by unique number?
As in a number that cannot be divided by anything other than itself and one.
Yeah, that is prime. But how do you know that there are infinitely? So you say. So how do you know that there are infinitely many primes? How do you know that if you list all primes, you could go on and on and on forever? No? No idea?
No idea, sir.
No idea. Okay. Okay. So now as a task for you, read out proof of theorem 3. in page 275 of the textbook. Yeah, read out the proof, yeah, and discuss it next on Wednesday. All right, try that. Yeah, try reading that proof first. Yeah. So and discuss it. I mean, what is the key parts and so on, right? Instead of me explaining it right now, right? Can you do it? Can you do it?
Yes, sir.
Okay.
Yes, sir.
Yeah, let's try that, and then let's discuss this next on Wednesday. So right. So in the meantime, let's have a look at the next part, GCD and LCM. So this is very interesting. I think this is related to the question we had about the I think one of the quiz, right? Yeah, the quiz solution. So so here is an example, right? So somebody wants to floor wants to tile his floor, and the problem is that so the room's shape is rectangular, so 20 by like this, roughly, right? Roughly like this. This 420 centimeters long, and this is 364 centimeters long. Now you want to tile this with as few tiles as possible, yeah, such that the whole floor is perfectly covered. So that means you have to somehow divide this as large as possible, and so also this part as big as possible, right? But you have to be sure that the tiles are all square. Now this is a problem that can be solved by using GCD. So you look at the GCD of the greatest common divisor of 2020 and 364. Can you guess? What is the GCD of those two numbers? Can you guess? Huh? Can anyone guess? What is the greatest common divisor of those 20? 28. Yeah, let's see. Let's keep this answer in mind, right? Let me put it. So that means if 28 is the answer, then Dobby needs 28 by 28 tiles. So this is 28 by 28. So how many numbers, how many tiles do Dobby actually use? That will be 364 by 20 divided by 28 times 420 divided by 28, right? Okay, but let's have a look, right? So what is GCD? GCD is called the greatest common divisor or greatest common factor, which is the largest integer that divides both A and B. So, for example, GCD of 36 and 48 is, well, 12, right? Because the largest integer that divides both 36 and 48 is 12. There is no bigger integer than 12 that divides both. What about GCD of 25 and 21? What is the largest integer that divides both? the largest integer that divides both 25 and 21. Answer?
1,
1. Why not 3? Sorry, why not 3?
because 25 can't be divided by 3.
25 cannot be divided by 3. That is correct. That is 1. So, now the first question then, how do we compute GCD? The first one that we can think of is, can we use prime factorization? So let's see. Write the prime factorization of 36, 48, and the GCD, which is, this is what? This is 12, and this is 1, and this is what? GCD of 120 and 500. It's 20, right? Yeah, I think it's 20. Yes. So let's see. 36 is what? To the power of 2 times 3 to the power of 2, right? Now 48. Can you give me the factorization? What will be the factorization of 48? To the power of
2 to the power of 4,
4 times
3.
3, correct. Now what about 12?
2 to the power of 2 times 3.
Correct. So what, can you guess now the pattern? How do we get 12 here? You pick which part? How do you get, where did we get to the power of 2 here? From? What is this? Is this a factor of 36 or 48?
36.
36, right? So actually it's both, right? So we take this. And then the 3 here, we take it from here. Right? So what about the next one? 25 is 5 to the power of 2. 21 is 3 times 7. And then the GCD is 1. Is 1. So now where did we get 1 here?
Because they don't have then
They don't have the same divisor.
They don't have the same divisor. Okay. What if I wrote it down like this? 3 to the power of 0 times 5 to the power of 2 times 7 to the power of 0. And then this is 3 to the power of 1 times 5 to the power of 0 times 7 to the power of 1. And now you see the pattern?
yeah.
Yeah. So you pick this, you pick this, and then you pick this. Which is then, yeah. Good. Now how about 2020? 500. And then GCD of 2020 and 500. Which is 20. I thought it's 20. What do you think? 2020 is what? What is the factorization? To the power of To the power of what? Under 20 is what? Anybody?
To do the power of 3
Yes.
times 5 times 3.
Times 3 times 5. Okay, let's write down this way. Let me put the power here. What about 500?
Uh, 5 to the power of 3
Okay, so
times
5.
2 to the power of 2.
Okay, then let me put this. Right. So what we take is, let's see, is it correct that 20 is this times this times this? Answer is
Yeah,
yes.
yeah.
Yeah. So 3 power of 2 times 3 power of 0 times 5 to the power of 1, which is 2. So the main idea here is that then to get a GCD, you factorize the numbers like that, and then pick which factor. You pick which factor. What do you think? You choose, you factorize both numbers, and then like put them all aligned, and then you pick which factors.
The smallest one.
The smallest one, the one with the smaller exponent, right? The one with the smaller power. Yeah. So that's the main idea of this theorem. So essentially, GCD A and B is you take the factorization like that, and then simply take the smaller one as the exponent. Remember, the power can also be 0, right? Can also be 0. Yeah, can non-negative means it can be 0. So we use that. Yeah. Now that is the way to compute GCD. Yeah, one way to compute GCD. Yeah. Now, hold on a second. I think. Okay. But now there is a way to compute GCD. Let me jump into that. This part. There is a way to compute GCD in a faster way. Yeah. Now, it's prime factorization. But the question is the approach efficient? The problem, it is not. Yeah. In theory, well, in practice, no, it's not efficient. Yeah. Yeah. So as of now, there is no algorithm that has been shown to be able to solve this prime factorization efficiently. So therefore, to compute GCD is very inefficient if we use prime factorization. So do we have another way? Well, fortunately, yes, we do have another way. It's called the Euclidean algorithm. So here is how it works. So let's compute GCD 21 at 78. Now, let's consider the integers 71, 21, 78, 21, 15, 6, 3, and 0. So can you see the pattern? Can you see the pattern? What is GCD of 71 and 78 and 21? Can you guess? It's, we use factorization. We know that 78 is actually 2 times
3 times 13.
times 13, right? And then 21 is 3 times 7. So the GCD is
3.
3. Yeah. Now, what about GCD of 21 and 15.
3.
3 again. GCD of 15 and 6.
Still 3.
3 again. GCD of 6 and 3.
3.
3. And then GCD of 3 and 0.
0.
What is the largest integer that divides both?
3, sir.
3. Yes. Be careful here. 3 divides 3 and 3 divides 0, right? Not 0. 0 does not divide 0 nor 3. Yeah, remember, be careful there. So, what is 15? If you consider 71 and 78 and 21, can you get 15 from 78 and 21?
No.
Use all operations. You can use multiplication, division, modulo, and whatever.
Yes, then.
So what? What do we have? 15 is what?
15 is
78 modulo 21.
Correct. So 15 is 78. Mod 21. Wow. Okay. So let's see something here. What about 6? Can we get 6 from 21 and 15?
Yes, 21 minus 15.
Minus. Or what about mod?
Yes.
Okay. 6, sorry, 15. So 6 now we have now 3 is 15 mod 6, right?
Yes.
Okay, great. Now, and then of course 0 is 6 mod 3, right? Yeah. So you see now, this part is the mod of the previous 2. This is the mod of the previous 2 and so on. So can we generalize this? Yes, we can actually. So that means if you have GCD of A and B is equal to GCD of what? If this is A, this is B, then
GCD of BC.
what is C then?
15.
No. So what is 15?
GCD, the GCD of
If 78 is A, if 21 is B, then GCD of A and B is equal to GCD of
B and A.
B and
yeah, of course. If this is what we want, then you have that GCD is 71, 28, 78, 21 is equal to GCD of 21, 78. Is this what we want? No, right? So we want to say that GCD of 71 and 20, 78, 21.
A mod B.
Yeah, that is correct. So what we want is this. If we use this, then we won't get smaller, right? So what we want is something like that. See? So that means we can reduce the computation up to 0, right? You get that. All right. So now that's the idea of the Euclidean algorithm. Let me stop here and let's continue on Wednesday with GCD Euclidean algorithm, and of course discussion on the proof of there are infinitely many primes. And then we'll talk about relative prime and of course one one of the quiz problem that are asked in the reflection. All right, so I guess that's it for today. Any question before I finish?
No, sir.
No. All right. So for the presence, for the attendance, no worries about that. We're still setting this up. There's a few issues with scaling. So until then, you don't have to fill out. Yeah. Or maybe by Wednesday, hopefully we'll resolve this out. All right. Okay. I'll see you guys then. If there's no question, I'll see you guys on Wednesday.
Thank you, sir.
Thank you,
Thank
sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Great.
Thank you, sir.
All right. So I'll see you guys. Bye bye.